All right, let's start all over again. This is a talk about the actor model and a crossroads of the actor model between also using domain-driven design. So hopefully I can give you a compelling reason to look into using both of these. One being more of a technological approach, the other being more of a strategic and tactical approach to implementing domain models. If you want to keep up with my latest work, I suggest that you follow me on Twitter. And here's a very interesting person. How many here know of Admiral Rear Admiral Grace Hopper? Okay, not that many actually, but Admiral Hopper was a computer scientist and actually writing software for a long time. You can look her story up on Wikipedia, but the interesting thing about Grace Hopper is that she was very much into not wasting computer cycles or network cycles or any sort of areas of performance. Now, she was practical in that she didn't expect someone to spend an inordinate amount of time tuning an insignificant part of their software, but she also emphasized not wasting nanoseconds. So I attended a live presentation of Grace Hopper's probably 30 years ago, and one of her famous maneuvers during her presentation is that she would hand out what she called a nanosecond. And a nanosecond was a piece of wire, like copper wire in a plastic coating about this long. And Grace Hopper said, this is the distance that light can travel in 1 nanosecond. And she said there are too many nanoseconds that are wasted by software developers, and she would admonish software developers to clean up their act, to write software that was the most performant that it could be in a practical way. Of course, on the other hand, we all know of Donald Knuth, and often Donald Knuth is quoted as saying, "Premature optimization is the root of all evil." Okay, a famous saying. And I think probably most of you here are aware of that statement by Donald Knuth and who Donald Knuth is. On the other hand, did you know that that's not exactly what Donald Knuth said? Not exactly what he said. This is actually what he said. We should forget about the small inefficiencies. Say about 97% of all the time, premature optimization is the root of all evil, yet we should not pass up our opportunities in that critical 3%. I'm going to argue that these days there's probably more than a critical 3% because of the sort of roadblocks that software that is not written to be highly concurrent runs into. And so I'll make an argument for concurrency in the age where concurrency is almost entirely necessary because of the kinds of hardware shifts that we've seen in production of microprocessors and so forth. But you know something else that Donald Knuth said? He said, people who are more than casually interested in computers should have at least some idea of what the underlying hardware is like. And then notice this. Otherwise, the programs they write will be pretty weird. So what does that mean? I think that applies today because possibly even more so than back then, but I remember when I started programming, close to, almost 35 years ago, and I had to be very concerned about the hardware that my software ran on. I was first writing professional software on the very early editions of the IBM PC. And we had dual floppy drives. We had an 8088 processor and normally just about 256 kilobytes of RAM. So being concerned with how software worked made the difference between a COBOL implementation on the PC. Believe it or not, you could write COBOL for the IBM PC 35 years ago, but it took 10 diskettes to hold just the executable pieces of the program, and whenever a portion of the program was not available on the diskette, a message had to be popped up for the user to change the diskette, for example, from diskette number 1 to diskette number 5, plug that diskette number 5 in, close the latch for the door of the drive, and then press some key to allow the program to continue operation. We took software, that very software, redesigned it using the C programming language, and we were able to contain the C program implementation of this on a single diskette, and we even added more functionality, business functionality, and even some technical maintenance and housekeeping functionality to that software, and it all ran completely in less than 256K, and it was very fast, and our customers loved it. So I think that we have to take Donald Knuth's advice in the day and age that we're living and understand that if we don't write software that has the potential for being concurrent in its solutions and also very distributable, then our programs or the software that we're writing can be pretty weird. We're all familiar with objects. I hope most of you are anyway. And when we deal with objects, such as the two objects here, a client object and a server object, we're used to the fact that when we make an invocation from the client object to the server object, that invocation will cause the client to block until the server finishes the request that we've made and returns whether it's a value or no value at all. Control goes back to the client, and finally the client continues to operate. This is a completely blocking environment. And so what we need to do is potentially shift our thoughts from a blocking environment to a non-blocking environment in order to write software for today's hardware that is not pretty weird. And this is why I make this statement. In the year 1973, look at the way processors were, what kind of processors was available. So the clock speed of most processors in 1973 was less than 1 megahertz. And there were probably about 7,000 to 8,000 transistors available. And Moore's law played out, which was actually stated in the 1960s, but it continued to play out for a long time in that processor speed continued to grow and expand, and so did the transistors, so that we were seeing, every year like a 100% speed increase in processors, or at least every 2 years, which was the prediction. Oftentimes it was less than 2 years. But notice in about the year 2003, so 30 years after 1973, the processor speed just basically tailed off. It doesn't mean that we aren't getting faster processors, it's just that we aren't seeing the kinds of processor speed increases that we did when we were under Moore's law as far as processor speed goes. Interestingly, numbers of transistors has continued to grow over time, but the clock speed of CPUs has not. So what do we do about that? What does that imply about the software that we write so that we aren't writing weird software? One of the things that really matters today is the number of cores on the processor, not the speed of the processor or the cores themselves. So while we see maybe a 30% increase in the one generation of a processor to another, like this Intel processor, what we generally tend to see is actually more cores. While they're not much faster cores, there are many more cores available. And so maybe when we start thinking about the number of cores available, we're going to say to ourselves, hey, I can write multi-threaded software. Finally, it's really going to count because I have a number of cores that I need to make the kind of process or progress that I need in concurrent software development. And so you get this idea that threading is going to be easy now and it's going to be efficient because of all the cores. But what do you think actually happens to many multi-core designs or multi-threaded designs? So here's our dream, right? We're going to create a work queue, like you see here, and this work queue has one thread that is feeding new work into the work queue. And so you could call this or refer to this as single writer, but the problem with this is there are actually multiple consumers to this. And this design sort of implies that we have at least 4 cores available. So we're going to have 4 threads running. One is feeding the work queue, and the other 3 threads are taking work out of the queue and working on it. Okay, that seems like a fair optimization to our software. It's very easy to design this and to make it work. We can all succeed with this, right? Actually, what happens with this kind of design before we know it is that we realize that sometimes the thread that feeds the work queue cannot operate fast enough to keep up with the threads that are taking work out of the queue. And what happens in that case is we have to start using synchronization, such as Java synchronization, to block so that any changes to the queue will not overwrite the point that where the worker threads are ready to go, especially if we're using a ring buffer. And other problems start to happen, like, in other words, there's only going to be one thread number 4, that is accessing in this particular scenario. And notice thread 2 and 3, which are also worker threads, are blocked, and the thread that's feeding the queue is blocked because thread 4 is reading it. So thread 2 and 3 are waiting to get their next work to do. Finally, thread 4 finishes, and let's say that thread 2 unblocks at this point and gets some work to do, and it goes and accesses an entity, and then thread 3 gets its next task to work on, and it accesses the same entity because there are 2 work items or tasks to perform on the same entity. Which one actually gets to the entity first, thread 2 or thread 3? Well, it's entirely up to the scheduling and how that works out. It could be that thread 3 accesses and gets its task after thread 2 and yet still makes its way to the entity before thread 2 does. It's possible. And so what we see is that thread 2 and thread 3 are both contending for tasks and contending for the entity that they want to work on. Essentially what's happened is we've turned our multi-threaded, very simple work queue into a single-threaded application. So really, when you think about it, multi-threading is not straightforward, and ultimately, there's also a statement that's been made among the really, let's say multi-threading or concurrency elite in the Java world that claims that most multi-threaded software written in Java is wrong. So what do we do about this situation? One option that we have is to use the actor model. The actor model allows a sender, let's say putting this sender into the client position. So it's the client, and the receiver is the server. So thinking back to that object example where we had both a sender client and a receiver server, the sender can send a message to the receiver or server, and the sender does not block. Neither does the server or receiver block. That is because messages are sent asynchronously. So instead of invoking methods on an object, we are sending messages to objects. But other than the fact that we've decoupled temporarily the exchange of requests between a client and a server, there's really not much difference between an actor and an object. In fact, someone who is noted as, if not inventing the idea of object-oriented programming, at least highly, highly refining it, and this is Alan Kay. And Alan Kay said that the big idea of objects that he had in mind was asynchronous messaging between the objects. And we'll come back to that thought. But shortly after Smalltalk 71 was released, as in 1971, in 1973, Carl Hewitt and some colleagues came up with the idea of the actor model. This was a design that was articulated far, far ahead of its time. In Carl Hewitt's day or in the beginning of the actor model as a day in 1973, as I noted before, clock speeds on processors was less than 1 megahertz, and there were about 7,000 to 8,000 transistors. So indeed, Carl Hewitt was well ahead of his time. Now, have you heard the statement before that it seems like with all technologies, all sort of revolutionary breakthroughs or innovations in technology and programming approaches, that there's always someone who discovers it in academia and then it's discovered again in industry. And this is actually, at least as I understand it, what happened with Erlang. So Joe Armstrong and others needed to solve some problems for telecommunications, and they came up with an idea that essentially was the actor model, although, again, as I understand that they had not read the formal papers and other industry material, literature on the actor model before. So in 1986, 13 years after Carl Hewitt and colleagues do their work on the actor model is rediscovered in industry. So a big step taken there. Now note that even in 1986, having multi-core was not an option, and even having many processors or even dual processors on machines was at least unusual. But by the early 2000s, such as 2003, when those processor speeds started to drop off, companies like Intel and others started to recognize the need to produce the ability to run multiple threads at the same time. And one of the first breakthroughs that we saw in that area was called hyperthreading, and then following that was multi-core. And Jonas Bonér of Akka fame came up with the idea to take the work that was done by Joe Armstrong and Erlang and bring that to the JVM and the Scala programming language. And then more recently, a new language has been written called Elixir, and Elixir runs on top of the Erlang VM, and that occurred in about 2011. So do you see the trend that we're starting to move to a prolific availability of multi-threaded support through the actor model to allow concurrency? That is because it matches what the hardware is allowing us to do. So this brings up the idea then of what is reactive software anyway? So reactive software has four basic tenets to it, or characteristics. One of those is that it is resilient, it's elastic. Another is that it's responsive. And all of these three capabilities are supported by the fact that reactive is message-driven. So are these messages command messages or event messages or just messages? Actually, it doesn't matter, because all of those concepts are embodied in message-driven. So responsive, this means that regardless of the growing demand on a piece of software at any given time, the software will continue to be responsive and produce results at the same rate that it was under less load. Resilient means that when a crash occurs in the software, that the crash is not cascading, it doesn't bring down the entire application or subsystem where the crash occurs. Now, tell me, by show of hands, how many of you actually know what to do with an exception when a service that you're using underneath, and I don't mean even necessarily a distributed service, I'm just talking about an object that you call on to do work, throws an exception? How many here actually know exactly what to do about that exception and how to make the object recover from the crash that has occurred to it and have a successful outcome regardless of the crash? Yeah, we agree. Usually what happens is the exception bubbles all the way up, even to the user interface, and the user is told, what you just requested didn't work, try again later. That's not very helpful, especially if we have a better solution for them. And resiliency in a reactive software implementation is quite important. And the reason for that is that the software, the client that calls on the service to perform a request in its behalf, does not have to deal with the exception or the crash that occurs on the server when you're using reactive. Instead, or especially with the actor model, instead, the parent component or parent actor of the child who crashes is the one who knows how to deal with the crash, help the child to repair itself, and then send it on its way to perform the action that it was intending to perform. And the only thing that the client actually has to worry about is, did I get a response? If I didn't get a response, then I'll ask again. And I'll just keep asking until I do get a response. Or there's some sort of timeout that occurs, but at least we can then give a kind of intelligent response to the user and allow the software to be both resilient and responsive. Elasticity means, of course, that a solution, a subsystem can grow and shrink as needed according to demand. And all along, this is all driven and sewn together by the ability to deal with messages as the messages occur. So why is the actor model so important now? Well, we have a lot of advances, and I did mention cores, multiple cores, but let's just think about the decreasing expense of storage, the decreasing expense of memory, the fact that networks are becoming faster, even more reliable. Even though we know that networks in general are not reliable, there are still networks that are much, much more reliable than we've been used to in the past. The fact that Internet of Things matters these days and will probably continue to grow in usage, where there will be many billions of connected devices, and all of these things are basically cheap. But to re-emphasize the fact that cores matter, note what can be obtained today rather commonly and without very much cost. So the Xeon processor, the Intel Xeon processor, can support up to about 88 cores, and then if we decide to go co-processor with the Xeon Phi, we can actually get 200 plus cores on a single processor. And actually, it's not even uncommon at all for processors to support teens of cores, or even 24 cores or 30-some cores. So even at that, we have the ability to run a lot of simultaneous requests and respond to those. The actor model also allows us to embrace latency. Whenever we introduce the network, we are automatically introducing latency, because as soon as we make a request over the wire, we don't know whether that wire is going to be fast. We don't know if the server on the other side of the wire is even going to be available. Is it clustered, or is it single instance, single node? We don't know. But one thing is for sure, if we design for latency in our software, latency will then not have a limiting and devastating impact to the operation of our software. And when we design for the actor model, we expect latency. There will always be latency, because sending a message from one actor to another actor always introduces latency. We will never get a blocking response back from another actor. So if we treat everything as actors, we are embracing latency and we are preparing ourselves for success on the network. Another thing that I like to point out, and I state this on a fairly regular basis. Some of you may have even seen a tweet that I produced a couple weeks ago. I saw this other tweet that was quite interesting, and the assertion by this developer was, "You are not Google." Do any of you remember that tweet? Maybe you saw it. And I said, I say this often, and it's actually rejected often. So many developers want to do things that put them at the scale, or at least allow them to pretend to be at the scale of Google, of Amazon, eBay, Netflix, and so forth. And yet, that's very rarely the case, that we're working in that kind of environment. And yet, why would we choose to use the actor model when we're not at Google scale? Frankly, it's because we can do more with less. If our solutions currently run on dozens, possibly scores of servers, even hundreds of servers, the chance is quite high that we could reduce the number of nodes involved in our solution down to just a few, because our software is running much more efficiently than it ever has before because of the use of the actor model. So consider the ability that concurrency and distribution gives you in the overall solution to actually simplify the entire topology that you're faced with on a day-to-day basis. So the actor model, as I said, supports direct asynchronous messaging. It's lock-free, share nothing. So there's nothing in the actor model that requires blocking or locking at all. The sender and the receiver of a message do not need to block in order for the message to be given to the sender. Even if there are multiple senders simultaneously, it doesn't have to block. And there's a share nothing environment where actors never pass out an internal reference to their state that allows another actor to twiddle with that state without sending in a message. So messages must be sent to get any state mutated in the entire system. An actor has the opportunity to prepare for its next message, which means that when one actor sends it a message, it can decide that its state has transitioned to the point where it can become another kind of message listener. And when it becomes this other kind of message listener, it will then be prepared to deal with messages in a different way than it would have under the previous state. This is called become if you're using Akka. And actors come in systems. As it said, one actor is no actor, as in Carl Hewitt making the statement, one actor is no actor. Actors come in systems, and therefore you may have a variety of ways that actors are represented as systems. In this case, like Akka is a hierarchy, and we set up hierarchies of actors in order to be resilient and provide supervision in a hierarchical way. And actor concurrency, of course, we expect concurrency, but this illustrates concurrency at a very interesting level. Do you notice the sequences that are occurring? Sequence 1, sequence 2, sequence 3, but wait a minute. There's a sequence 2 and a sequence 3 down there. Did I make a mistake with this? No, what we're talking about is that the number 2 sequences are happening simultaneously. As the router actor is asking for a scheduled event, a timer event, to be registered for the router itself, the router has also already sent a message to a receiver, and the receiver will react, and now there's a race condition. And I don't mean a dangerous race condition, I mean an optimal race condition that says, will the timer time out, and will I get a message that tells me that the timer timed out before the receiver of the message provides a reply, a successful reply to me. If I get the timeout message first, it means that we're going to tell the client that we failed or timed out. If we get the receiver's reply first, we're going to tell the client that it succeeded. Now, when we use actors, how many actors do you think are practical? If you're thinking in terms of maybe some kind of messaging mechanism, it might sound to you like, well, if I had 50 message listeners in my application, that might be all that we can deal with. Maybe we even have 100 message listeners, so we have a bunch of competing consumers spread across our particular subsystem. But actually remember that actors are very much like objects. In fact, they're just like objects, except we do not invoke methods on them, we send them asynchronous messages. And so actually having 1 million or more, maybe even several million actors in a single VM is not unusual at all. So actors scale. Another thing that can be daunting for a software team is the fact that the architecture of a typical Java sort of n-tier or multi-layer solution can be quite complicated. This is called a ports and adapters or hexagonal architecture, or maybe you even call it the onion architecture. But look at all of the components that a programmer needs to understand and become expert on in order to use this kind of architecture. So we look at it tipped on its side, and there are a lot of different concerns along the way that we need to learn how to deal with. With the actor model, however, I think that this produces the opportunity to have what I call the simplicity stack, where literally we have a UI with controllers backing the UI in our simplified architecture, and literally the controllers can be the components that hand off messages directly to the domain model. And you may be concerned that this is going to make the controller method very busy. Actually, you can write a controller method that's 5 or 10 lines in length easily, probably even mostly 5 to 7 lines of code that will handle this entirely without any problem at all. And once the actor domain model object has control by means of it receiving and processing a message, what it can do is simply emit an event, and therefore we have a command event based architecture which is message driven, which is resilient, elastic, and responsive. So how do we cross the bridge over into DDD land with actors? So we of course have Eric Evans' seminal work on domain-driven design, and his book that continues to sell at near #1 rate in its category on Amazon, which means it's really picking up popularity, and not just popularity in terms of interest, but popularity in terms of full recognition that DDD matters today, and it's helping a lot of teams to succeed. So we can use the essence of domain-driven design, such as the bounded context and a ubiquitous language within a bounded context, which gives us a semantic understanding of the components that operate inside the bounded context. And as they do so, we understand as a team everything that works in our domain model works because we have built a language around that, the semantics around that, and it's not only the object names or the class names or the actor names, it's also the names of the operations and the deep understanding of the business sense that's involved in having a model that works beautifully, if you will, in terms of what the business needs and the mental model of domain experts. You also have the ability to map various bounded contexts. Since you are using smallish bounded contexts with domain-driven design, you will always have multiple bounded contexts or even unbounded legacy systems such as big balls of mud that you're going to be integrating with. And when you do that, you're going to need the strategic design tool called context mapping. So there is a bit of detail involved in understanding these two major concepts around strategic design of DDD, and I suggest that you look into those. They're very powerful tools. So today, I think that what we face as developers is a demand to keep up with the churn of business, where the business doesn't just churn on the same old ideas, but the business churns on brand new ideas, even on a daily basis. How do we keep up with that? How do we make releases to the new ideas, the demands for new business direction? I think that domain-driven design is an excellent way to tackle or make the complexity surrender, and we tame the complexity of these new business concerns. And as we tame the complexity of these, we're doing so through knowledge crunching. We're learning every day about what the business needs in order to succeed, and not only to succeed, but actually to be prominent in the direction of their business. And actors can allow us to make rapid progress on this. When we shrink down the architecture to a very simple architecture, it can help us not only to reason better about the software that we're producing, but actually have less moving parts and focus on the actual business aspects of the software rather than all the architecture that's surrounding it and all the components and layers and the need for massive garbage collection that we fall into many times. So think of the actor model actually as a way to accelerate your development. And here again, I need to emphasize that Alan Kay, the inventor of the Smalltalk language, said that the actor model retained most of the ideas or what he thought were the good features of the object idea. So the person who invented object-oriented said, this is what it's really all about. And you know when he said that the big idea is messaging, Alan Kay said that there's this Japanese word, I think the word is ma, or something like that, roughly spoken, but ma means the space between. And maybe even Conrad is here. He could correct my Japanese if I'm wrong about that. But as I recollect, it means the space between objects. And so he is talking about the fact that messages between objects is the really important thing, not the implementation internally of the object itself. And actually, we put so much thought and so much energy into the internal implementation and design of objects that sometimes we forget that really the most important thing between objects is the ma, or the space between, that is communicated on by sending messages between them. And so because of that, we have the opportunity to implement the ubiquitous language for a given bounded context by use of actors, by actors sending messages, and the messages actually reflect the spoken language that our team shares together. So for example, we have a command message incoming to an actor, and the actor produces another message, which is an event message. All of these messages are very, very important because they carry the ideas of the ubiquitous language, and in addition, the product and the backlog item actors that are involved in these two stories or use cases or scenarios are themselves part of the ubiquitous language. How do we do DDD then? I mean, you know, oftentimes we wonder, how should we use domain-driven design in a real project? I think that these sort of 5 points are the most important, at least to me they are. DDD is about talking to your customer, whether your customer is a colleague in your own company or whether your customer is outside at some other business that you consult with. And once you talk to your customer, you should be able to write some very straightforward scenarios about what their business is looking for. We iterate on everything that we do, including the scenarios. Maybe we can actually produce only 2 or 3 scenarios, or maybe just a few more, and from that it allows us to get into a strategic level of event storming. And then as we iterate on that, we're getting a deeper and deeper understanding, and then we can go into a tactical level of event storming, which again is iterative, and then finally we are working on implementing acceptance tests and the model code, where we're actually projecting the ubiquitous language right into the domain model. And we're iterating on that as well, and we continue to iterate on all of this, having more and more conversations with the business. So this is event storming. You can read more about it in my distilled book. There are other resources available online for understanding event storming. And I'll be going into this more tomorrow in my lab at 9 o'clock in the morning. But essentially, we take the design level event storming and use that to implement aggregates or domain-driven design aggregates as actors with the use of command messages, event messages, and we iterate on that. An interesting approach to implementing an actor internally or a domain object internally is to try to make most of the internal parts of the actor immutable. Because actors are naturally mutable state, we do have to allow some things to mutate, but we can limit that down to actually just one variable, and the rest of the actor state can be treated as immutable, in fact, in a very functional way. Transactions are controlled by the aggregate itself, so we don't need a transactional layer above the actor, and we're emitting a corresponding domain event which can be used in an event-sourced way. So here's a brief look at an Akka persistent actor that is fulfilling the role of an aggregate named product, and this actor allows us to bring in or accept an incoming command message. It translates that to the corresponding event and then emits the event that will be stored, and it will also represent the state of this actor internally as the stream of events builds up. And we can mutate the state. As you can see, this is done in a very functional way where we're replacing the previous state with a new state, and yet the actual product state object itself is immutable and used in a functional way. So this is as simple as a client can be, and think of this as being the client at the controller level. We simply send a message to the product after getting a new actor product with a unique identity, and that message is handled as an incoming command which will then produce an event. And from this we have the ability to then interact with different bounded contexts, and as we do so, we're translating one ubiquitous language to another ubiquitous language as the messages cross context boundaries, and so our reactive subsystems or reactive services build up into whole reactive systems. Now, one thing that I have neglected to warn you about is that when you start developing reactive systems as a whole, we have to say hello to uncertainty. In fact, we have to embrace uncertainty, and I'll be talking more about this down the road. I'm not going to go into detail right now about that. But here's a resource that I have. If you don't have the opportunity to attend my lab or workshop tomorrow morning at 9 a.m., then take a look at this GitHub repository, which has a set of slides that basically matches this presentation, roughly speaking, and it shows you actually how you can use domain-driven design with actors in at least 4 different languages and 4 different actor models. So one is Scala with Akka, another one is C# with .NET, another one is Elixir, and another one is pure Erlang. So that's all that I had today. I hope that this has been instructive. You can read more about domain-driven design. I have quite a heavy-duty reference called my Red Book, or Implementing Domain-Driven Design, and I have my distilled domain-driven design book, which has been released for roughly a year, and then also a book that gives us a good idea about how to use the actor model. So I welcome questions afterwards, but we need to end this presentation now. Thanks again for attending.